Hello guys, today we're gonna talk about more about MASM programming, assembly language programming. We took there's a lecture posted on YouTube before this. It's called Introduction to MASM Programming, Assembly Language Introduction to MASM Programming. So this will be lecture 2, Introduction to MASM Programming. A couple of things we need to know. We covered most of the stuff. We took 2 examples over there. We wrote them. Today I'm gonna go briefly over a couple of things, and then we start. Types of operand, and this is really important. What do I mean by operand? If I have a move, like move EAX, EBX. EAX and EBX are 2 types of operand. EAX. Okay, here I've got an error here. It's EAX. 2 types of operand. 2 operands. Both of them are registers. What other types of operands do we have? We have registers. EAX. Here's supposed to be EAX, AX, AL, AH. Remember, this is what? 4 bytes, 32 bits. This is 2 bytes, 16 bit. Lower 8 bit, higher 8 bit. We have memory location. Like num1, total size, all those variables that we declare are labels or memory locations. We have constant values or immediate, sometimes we call them 10, 20, 1000. Those are all constant values or constant expression. 10 plus 5, that's an expression of 2 constants. This is an operand and this is an operand. That's what they mean by types of operand. This is an operand of an operation. This is an operand of operation. We can have either a register, a memory location, or a constant, depending on the command or instruction. Registers. We have in our x86 architecture. We're gonna talk about 8 registers, 8 general purpose registers. 4 of them which we can divide into 16-bit, EAX, EBX, ECX, EDX, accumulator, base, counter register, and data register. E stand for extended accumulator register, extended base register, extended counter register, and extended data register. Each one of those we can divide into 2 halves. Each one of those is 32-bit, so we can divide them 16-bit, 16-bit. If I divide them into 16-bit, I can't use the higher 16-bit. I can only use the lower 16-bit, which is called AX or BX or CX or DX, and I can use either an 8-bit high or an 8-bit low. AL, AH, BL, BH, CL, CH, and so on. I have another 4 general purpose registers, but those are used for special uses like extended source index, extended destination index, and EBP, extended base pointer for the stack, and extended stack pointer. And we'll go over those when we talk about stacks. We're gonna use those ESI and EDI when we talk about arrays, so we'll cover those lately. 2 dedicated 32-bit registers. I have the EIP, extended instruction pointer, which holds the address of the next instruction to be executed. So we bring the address of the next instruction. Address where? In memory. Memory, what do I mean by memory? RAM. I put it in a register. Why do we put it in a register? Make it faster, so we can grab the address immediately when I finish from the first instruction, or the CPU is doing that. The CPU grabs the address from the extended instruction pointer. Sometimes they call it, in other architecture they call it PC, program counter. The E flag, I have a 32-bit register, each bit representing a flag, like a 0 flag, parity flag, sign flag, carry flag. Every clock cycle the CPU looks at that flag and checks if any has changed, and this is really important to keep it in mind. and we have also 6 segment registers. Each of them is 60-bit. We have the code segment, data segment, stack segment, and 3 extra segments. We're not going to be using those, but code segment will hold what? The segment of the code, where the code is. DS will hold where the data is, 16-bit. ES will hold where the SS will hold where the stack is. Stack is really important. We're going to take some examples on it later on. So now let's see. We have total of 10 32-bit registers, 8 general, 2 dedicated, and now we have 6 16-bit registers. So 16 registers in total. MASM instructions. Those are really important to know the instructions. If we don't know the instruction, we're not going to know how we're going to use them. So we have the move instruction. Move source to destination. So I'm saying whatever I have in the source is equal to the destination. Those are my operand, which we talked about them at the beginning. 3 operands. It can be a register, memory location, and constants. But we have some restrictions on the move instruction. No more than 1 memory operand permitted. That means this is a memory operand, num1, total, num2, if you remember. No more than 1 memory operand permitted. So I can move from 1 memory operand to another. This is not allowable. We can't do this. We can't do that one. CS, EIP, IP cannot be destination. That means I can't move to them. I don't want to lose what? The flow of the program. Meaning if I had extended IP, I'll have an address there. If an address of the next instruction, if for a reason we change the address, it will mess up the whole flow of the program. So this is not allowable. We can't. There's no way we can access EIP, IP, or CS using this move instructions. We can access it in another way, and we'll cover that later on. Destination can't be a constant. I can't move what? From accumulator to 10, or from 10 to 10. A constant to a constant, or from memory to a constant. Why I can't move to a constant? A constant is neither a memory location or a register. So if I move to it, where am I going to save it? This is not saved. This is not saved. One minute. What, Daddy?
Oh yeah. Oh yeah. No. Oh yeah. Uh-huh.
1 minute. Let's see. It's okay. The recording. Yep. Okay guys, sorry, my kid came in. Now we stopped here. Destination cannot be a constant. I can't move a memory location or a constant or a register to a constant. I can't say 10 equals EAX, but I can say EAX equals 10. That's different. So constant can't be a destination. No immediate to segment move. Segment moves, what are the segment registers? The 6 16-bit registers. Those we can't move to them. No immediate value, meaning constant or constant expression. 10 plus 10 plus 5, 10 plus 20, those are all constant expressions. And CS, DS, SS, ES, GS, those we can't move to them. We can't move immediate to them. Size mismatch. Move byte, byte. Move word, word. It has to be, meaning this has to be a byte. They have to be the same size. I can't move 1 byte to 2 bytes, or 2 bytes to 1 byte, or 3 bytes to They have to be the same size. Here what do I have? I'm trying to move A8, which is what? 8-bit. 8 higher bit of the accumulator. This 8-bit. This is A high. I'm trying to move it to BX. BX is what? Those 16-bit. So I'm trying to move 1 byte to 16-bit to 2 bytes. That's not allowable. Invalid. And here I'm trying to move BL. BL is the lower 8-bit of EBX. And I'm trying to move it to 16-bit AX. And that's not allowable. 1 byte to 2 byte. Those are really important, guys. Those instructions are important for programming. So that's the move instruction. Now we have another move 0 extended. This is 0 from here, 0 extended, and this is move sign extended. So what's move 0 extended and what's move sign extended? Here we can have, for example, 1 byte. I'm moving it to 2 bytes, but this is not the move instruction. This is the move 0 extended, meaning I move this source which is 1 byte BL to AX, which is 2 bytes, and I fill the upper 1 byte, the one remaining 1 byte, with zeros. This one move sign extended. I'm moving, for example, this can be 1 byte, 2 bytes, and I'm moving it to 4 bytes. If this was 1 byte, I'm filling the rest of the 3 bytes with the sign. It's either 0 or 1. If the sign was 0, I'm filling it with 3 bytes of zeros. If the sign was 1, I'm filling it with 3 bytes of ones. If I had 2 bytes, I look at the bits 16 or 15 if I start with 0, and I see, is it 0 or 1? If it's 1, I fill the rest of the 2 bytes with ones. If it's 0, I fill the rest of the 2 bytes with zeros. Destination must be a register. In the move 0 extended and sign extended, there's only one rule. Destination, which is this one. This is a destination and this is a destination. Must be a register. I can't have it either a memory location or a constant. And that's reasonable because memory location are already saved. So if you save num1, it's already saved as 2 bytes. If I try to extend it, I'll delete the data after that. I'll lose the data. That's it. On a constant, there's no memory location, so where am I gonna extend it? We have the exchange command or instruction. So now we have move 0 extended, move sign extended, and exchange. Operand 1 and operand 2. And this acts like 2 moves. For example, at least one operand must be a register. This is one of the rules. Why? I can't have 2 memory locations. I can't be moving between 2 memory locations. Remember here in the previous one, we can't have num1 and num2. No more than 1 memory operand permitted. Here at least one operand must be a register. Same size mismatch also applies. No immediate permitted. I can't have immediate because I can't. What's exchange? Exchange AX and BX. What I'm saying is move what? Actually we say doing move, and let's have a temporary value, temp, or another register, and I'm moving it to it what? Let's say EBX. BX. Oh, the slides are not enough. And then I move what? EAX to where? To EBX. EBX. Sorry, this one handwriting is bad. And Then I move what I have in temporary, and I put it where? In EAX. Temporary. Let's name it TM, and which is temporary at the top, which is this one, and I move it to EAX. Let's say I had in EAX, for example, 10, and I had 20 in EBX. This is AX, EBX. So I'm moving EAX to temporary. I'm moving 10 to a temporary value. Let's say this is temporary, T, and this is EAX, and this is EBX. And I give it an A and a B. So I moved 10 to temporary. Then what happened? I moved AX to EBX. Oh, this is EBX. Okay, I moved. Okay, sorry. I moved EBX to temporary. Then I move AX to. So instead of 20, now I have 10 in EBX. And now we move temporary back to accumulator. So instead of this, I'll have 20. So I exchange those two values. Size has to be the same, so I can't say EAX and what? And BX. I can't exchange EAX and BX. At least one memory operand must be a register. I can't have two memory operands. I can't have a constant. No immediate is permitted. No immediate is permitted. Let's see, MASM instructions. We have now the add and the sub instructions. And what does the add do? I have add AX20. And what exactly is this? This is the source and this is the destination. I'm saying what? AX equals whatever is in AX plus 20. So add whatever is in AX to 20 and save it in AX. So if I had 10 here, what is it gonna do? It's gonna do 10 plus 20 and save it in AX30. Now sub, same thing. This is a memory location. I have what do we have? num1, sorry, equals num1 minus 20. Oh, there's a cut here, but we don't see it. So if num1 was 40, I'm saying subtract 20 from 40 and save it again in num1. Overwrite num1 with the new value. Same as the move instruction rules. So what are the move instruction rules? First, no, at least one memory operand permitted. So I can't have two memory. I can't say num2 minus num1 or sub num1 num2. I can't have subtract from segment registers, so I can't have CS sub CS20. I can't subtract or add to EIP and IP, which holds the instruction pointer, the address of the next instruction. I can't have the destination as a constant. Destination can't be a constant. It's really important, those rules. And the size mismatch, I have to have them the same size. I have another two commands or instructions. Increment, and this is the destination. Increment ECX. What does this do? What I'm saying is ECX incremented by 1. ECX equals what? ECX plus 1. This is what I'm doing. I'm adding 1. Here I'm decrementing 1. So num1 equals num1 minus 1. I'm decrementing by 1. Decremented and incrementing. This is, so here, think of it. Can you increment or decrement a constant? I'll leave that for you guys. Now MASM instructions, the flow control, or what they call branching, either looping or if else in C++. So jump, I can have Gaith. This is a label of the code. I'm labeling my code, and here I can have a move instruction, for example move. I can have an add under it. Think of it compared to C++ and C, and here I can have another move, for example, whatever you want of instruction. Think of it as the loop, as the body of my loop. This is the curly braces and the body of my loop. I label it. I say Gaith colon, everything comes after it is in the body of the loop, or the branching, and I say here loop back to Gaith depending on some condition. What's good in the loop instruction here is what? Loop does this by default. What does it do? It checks if ECX, the counter register, doesn't equals 0, jump or loop to what? Go back to Gaith here, and it increments the accumulator ECX. So if I had ECX as 10, how many times is it gonna loop? 10. It's gonna do what? First ECX, if we said ECX equals 10. Here if I had move ECX as 10. So now I say what? Gaith label, do this instruction, whatever it was, whatever this was, comes here, checks loop, what? Does 10, if 10 doesn't equal 0, not equal to 0. Here I should have put an equal sign, but if counter register doesn't equal 0, go back to Gaith, loop to Gaith, and increment ECX by 1. So now ECX 9. 9 comes in, does this, checks, does it, 9 not equal to 0, jump. 8, 7, 6, 5, 4, 3, 2, 1. 1 will do it and exit. The jump is unconditional. This is conditional. Jump will jump wherever we had. It doesn't check. So if I had Gaith, jump to Gaith, it has to jump to Gaith. It doesn't check ECX. It's not like loop. But so what does that mean? If I leave it like this without any exit condition, it's gonna give me an infinite loop. Using jump, it's gonna give me an infinite loop if there's no way we can exit from this. We have another instruction, which is the compare instructions. The compare instruction. And we use it before the jump less or equal, jump greater or equal, jump equal, jump not equal. So we have all those. Meaning what? I compare two operand. They can be equal. One can be greater than the other, and or less than the other. So depending on the condition, jump less or equal, jump greater or equal, jump equal if they're equal. So before using any of those, we have to use the compare, so we can know jumping on what, less or equal. What's less or equal? Whatever we have in the compare instruction. So we finished those. Let's go now. I want to give you some really good examples on this, and guys, this is really important for the final. Really important for the final. use the following data declaration. Assume that the offset of the byte value is 000. So I'm gonna start with this address, my memory. And this time, remember in class I started with memory this way, going up. Now I want to start it from here. Some people start it vertically, like we'll have the memory flipped and we have it going this way and that way. We don't have it as we'll have it vertically laying down. Let's say this, I'll lay it down here, but I want to show you this way. And this way it's gonna be easier to apply a little Indian, but harder to apply big Indian. So let's see. I have a byte value. I declared a variable called byte value, and I'm starting with this address. So this is gonna be my first byte value. This is the second byte value. This is the third, but let me change this, and I want it to be in the middle. It looks better, the alignment. So okay, I left those here so we can add. Those are in decimal. 1, 2, 3, 4. By default, assembly will take those as decimal. So how will it save it exactly? I put 1 here to make it easy, but it's gonna save it as what? 1, 2, 3, 4, 5, 6, 7, 8, or 7 ones. This is 1, and I had a problem with this. No, I don't wanna. Why is it not showing it? Is it because of the alignment now I can't change the side? Shouldn't do that. Oh no. No, go back. No. What is it doing? So it's gonna be this 1 byte. This is a byte addressable memory, meaning every byte, this is my memory, a byte. Every byte is gonna have a unique address. 1 byte. A word addressable, every word. So I'll have 2 bytes here. And remember, this is my memory. I'm just showing you what here. How is it exactly saved in binary? This is 1. 2 will be what? How will I have 2? It'll be 0, 0, 0, 0, 4, 5, 6, 7. This is 2. 3 will be what? And I'm not going to be writing it in binary from now on. I'm just showing you to make it so you can understand what's going on the binary. It's not saved 1, 2, 3, 4. It's saved this way in binary. But I'm going to be writing it this way. It's easier for us to read. So this is byte value. Here is going to be a label. Remember, this is going to be labeled as byte value, which has the address 000. And now I go to word value. Word value will start here, and each one of them is declared as a word. And if I'm applying little Indian, what does it say? The least significant byte at the lowest address. What's the least significant byte out of this? Because this is the first element. The least significant byte is the byte with the lowest value. So here I'll have 00, and here I'll have 10. That's little Indian, least significant byte at the lowest address. That's, and because this is hexa is what? It's 4 digits. This is the first 0, and that's 0 0. And if I want to put it this way, the 10, this is gonna be saved as well. This. And this is big Indian. How is it saved? It's gonna save the 10 here and the 0 0 here. Big Indian or little Indian. This is how data is saved. Here I don't worry about little Indian and big Indian because here I have a byte, so it's not gonna care about it. Here I have a byte addressable memory and I have a word to save in a byte, so I'm gonna break it down to 2 bytes. So I need to know which byte to save first. And little Indian says we have to save the least significant byte with the lowest value at the lowest address, 04. Now about this, here I'm gonna save what? 0 0, 0 0, which is this, and 20 here, and this is gonna be 0 0 and 30 here. And now I'm gonna have 0 0 and 40 here. Now I'm gonna have a D word. A D word is 4 bytes, so this is gonna take 4 bytes. Each element from my, all of this is gonna take 8 bytes. So let's see, and I'll save it what? Lowest significant bit at the lowest address. This is the lowest address. 7 8 5 6 3 4 and 1 2. That's what. And that's the D word. Let's give it a color, a different color. And those are what? I should make it lighter a little bit so it doesn't confuse us. Okay. I don't know why it's not taking it by itself here. Oh, I left even the first one, so this is gonna be, let's change the background better. Those then I make it blue so it will stay there. So this was, how many bytes is this? 1 2. It's a word with 4 elements. It's gonna be 8 bytes. 1 2 3 4 8 bytes. And this is the first element, which is this. Let's try to match it. Oh no. I'm just showing you so you can see, and those will be that one. Oh, that's really good at it. Okay. Now what will we have here? We're gonna have lowest significant byte at the lowest address. 90 here, okay. And here's 7 8. And here we're gonna have 5 6. And over here we're gonna have 3 4. Little Indian, remember guys, what is Little Indian? Okay, here's the second number. Now I have those, a string. Here I declared a string, A B C D, EFD and a 0 null terminating character. So this is gonna be 1 2 3 4 5 7 8 bytes. I didn't have that much space for it, but we can add rows here. So here I'm gonna have A, B, C, D, F, and what did we have? G and 0. And let's have it as okay. It's really important, guys, to add the oh no. It's really important to have it, to have the 0 null terminating character at the end to indicate it's a string. And now I'm gonna change it to the label, meaning this is gonna be the byte val. This address, it's gonna take the address 000, and I don't want those. And this is gonna be, or you can think of it plus 0. It's gonna be plus 1, and this is gonna be plus 2, and this is gonna be plus 3, and this one is gonna be word, and I'm not gonna put it all, I'm gonna put val. So I didn't put the ORD, guys, just pay attention, but it means word val. And this is gonna be, think of it as plus 0, this is gonna be plus 1, plus 2, I was taking all of them like that, plus 3, plus 4, plus 5. Why is it 1? Incrementing each byte byte addressable memory. Don't think this is what, just a 7-bit. It's 0 to 7, which is 8. 0 to 7, which is 8. And I think we do this in my work here. Okay, and what is this gonna be? This is gonna be D word, and I'm gonna have a D val 1 plus 1, and the second element is gonna be, this is, or plus 0, sorry, and it's gonna take, the first element is gonna take 4 bytes, 1 2 3 4, and here I'll have D val plus 1 plus 4. That's the second element, and those are gonna be what did we name the string? It's gonna be a string, or okay, so I'm gonna have here a string, this is capital, plus 0, plus 1, plus 2, and we keep going to plus 3, plus 4, plus 5, plus 6, plus 7. That's plus 3. So let's check this. Use the following data declaration. Assume that the offset of that is, and that all code runs in protected mode. Let's see. I have moved. AX is what? 2 bytes. I'm trying to what? Move it to byte value. I'm trying to move byte value, which is 1. I'm trying to move 1 to AX, which is 2 bytes. So this is not valid. And here I'm gonna put the not valid as what? As red. Let's put it as red. This is a not valid. Not valid. It's gonna give us an error. This is what we mean by not valid. Instruction not valid. Now here I'm trying to move a word val, which is gonna be the first element, which is this one, the 1000. I'm trying to move this where to DX, which is a 2 byte also. So this is what? Valid. No problem. Here I'm trying to move a D word val, and this moves what? And let's put what does it move? DX is gonna equal 1000 hex, which is gonna be the first D. Okay, and here I'm doing D word val, so it's gonna be this one to ECX. This is also valid, and I'm gonna have ECX equals what? The first, and we don't worry about what, how is it gonna take it from here. What it does, the compiler or the operator inverts it, or the CPU inverts it back to the original value. So it's gonna go here, take 1 2 3 4 5 6 7. And why did it least significant byte at the lowest address? Okay, yeah. Now I'm gonna move a string, which is gonna be actually this one, a string to SI. Is this valid? Could be, could it? Not valid. Why? I'm moving a character into SI, which is ESI extended, which is can we break SI to 2? Or if we can break it, I can move 1 byte to 2 bytes. Not valid. So this is, let's mark it as not valid. Didn't use the red, I used this color. Okay, now I'm moving offset a string, meaning the address of what? This string. So what's the address of this string? It's gonna be, this is gonna be, don't think this 11 or 10. Remember here we went from 9 addresses on hexadecimal to 10, which is A, to B, which is 12, C13. So here I'm gonna have 1 0 1 2 1 1 1 2 1 3 1 4. So here what I'm doing is, where did it go? This one. What I'm doing is I'm moving to ESI the address of the string, which is 0 0 0 0 1 2 1 4 12 30 12 30 1 2 1 3 1 4. Okay, yeah. Now I'm moving the offset, and now here I'm moving what? byte value to AL. Byte value, so it's gonna move 1 to AL equals 1, and that's allowable. Why wasn't this allowable? Because this was 2 bytes AX. I'm moving 1 byte to 2 bytes. Here I'm moving 1 byte to 1 byte, and the 8 byte of AX are actually gonna be, remember, this is a 1. Do I have it right? It should be 7. Okay, yeah. Move EAX offset of what? I want to move the offset of byte val of this address to EAX. So EAX will hold what? And we should know that by default because we started with the address 0000. That's the address, the starting address. Now I'm moving DX, or I'm moving word value plus 2. Word value, where's word value? And I prefer looking at memory. That's why memory drawing is really important. Word value plus 2, which is this one, 00, meaning the second element. I'm moving it to DX, meaning this is val 0, word value 0 and 1. This is word value 2 and 3, which is this. So I'm moving the second element to DX to the data register. So DX equals what? Now I'll have 2000 hexa. Those are hexadecimal numbers. Okay, now what do we have? Move ECX. I want to move the offset of D word value. D word value, the offset of this, where the address of this in memory. Where's the word value? D word value. This one. The address is this. I'm moving it to ECX. So I'm gonna say ECX equals 1, 2, 3, 4, 5, 6, 7. See that address. Now I'm moving to SI. What do I do? What am I moving? Oops. I'm moving to ESI or SI, which is 2 bytes. I'm moving a D word value, 4 bytes, not valid. And we can't split not valid. Let's say size mismatch. I'm moving 2, or I'm moving 4 bytes into 2 bytes. Same here, size mismatch. Here also size mismatch. Those are the only ones on that not valid. So this, mark it as not valid. Okay. I think that will make it look better. Taking it them all, or did I change the color of that? So now let's go to this. Move ESI. I'm moving the offset of what? A string plus 2. The address of A string. A string is here. We had an address of 1414, not 1414. It's different. An hexadecimal. And I'm moving it to +1, +2. I'm moving this address, which is going to be ESI equals 0000451616. Now let's see. I'm moving offset of byte value +1 to AL. Byte value +1 to AL. Can I do that? Is that allowable? Why is this not allowed? Not valid. Size mismatch. Why is it size mismatch? Let's take it. Offset is what? How are you gonna know how much is an address? They told us, they gave us here, it's gonna start with this address. So this is how many each one of those is what? Is 4 bits. So 1, 2, 3, 4, 5, 6, 7, 8. 8 hexadecimal numbers multiplied by 4. Each hexadecimal number is 4 bits. So I'm gonna have 32 bits. So 4 bytes. Address is supposed to be 4 bytes. I'm trying to move it to what? 1 byte. No way. Not valid. It's gonna give us an error. Now I'm moving offset of byte value to AX. Yeah, that's acceptable. So I'm gonna move to AX. Why am I gonna move? Where's byte value? It's gonna be address 000. Should be 8 zeros. Now here I'm moving word value to DX. Word value is gonna be what? This 10, the first element. Word value, the first element. So 2 bytes to 2 bytes. That's valid. I'm moving to DX equals 1000 hexa. Remember, it's gonna be stored in binary, but I'm doing this. It's easier that way to read. I'm moving to ECX D word value. I'm moving 4 bytes D word value, which is those. So it's gonna be ECX is gonna equal 1, 2, 3, 4, 5, 6, 7, 8 hexa. I'm moving all this element, one element of. Now I'm moving ECI offset word value offset, which is 4 bytes, word value to ESI. What's the offset of the word value? Is gonna be this number. I'm moving it to ESI. So okay, now I'm moving what? The offset of A string to ESI. I'm moving here that address, same we took. Are they repeating those? Are those repeating? No, but I have a similar one like this. Why do you do it again? Okay, let's take it off. Now move to AL. A string plus 2. A string plus 2 is this. The address of A string, the offset, plus 2 is gonna give me, the address is 14, plus 2 is gonna go to 16, which is C, and I'm gonna move 1 byte to 1 byte. That's valid. Now here I'm gonna go offset of D word to EDI. Word value. Okay, so D word value, so it's gonna take this address and move it to EDI. So EDI will equal 0, 0, 0, 0, 4, 5, 6, 7, and here I'll have C. And now I'm moving what? Offset of byte value plus 2. What's this? Offset byte value is gonna be the first element, plus 2 is gonna be this. So I'm moving 3 to EAX. Not valid, or okay, I'm not moving an element, I'm moving the address of the, so it's gonna move to EAX. If it was the element, I can't, size mismatch, but I'm moving this address, the offset of this to EAX. Now I move word val plus 4. Word val plus 4. Where's word val? Here I have word val plus 0, the first one, plus 1, plus 2, plus 3, plus 4. I'm gonna take what? This element, the third element, 3000, and I'm gonna move it to dx. So here dx equals 3008, and here I'm moving what? dval plus 4, which is this. I'm moving it, those is gonna be 3 4 5 6 7 8 9 0 in ECX. And now I'm moving what? ESI offset of word value plus 4, word value plus 4, it's gonna be this, the address of this, I'm moving it to ESI 00008. I'm moving it to ESI. That's valid, no problem. Guys, it's really important to understand this, what's going here. It's really important. And let's say here I'm moving AL to AL, I'm moving C T to AL. It's the memory drawing is really important. Memory layout, really important. You're gonna have a question on that in the final for sure. Now let's check this. What is this asking for? We want to do those and check what's inside this. So now byte, I have a byte in binary, so I can save it, no problem, as a binary. If I want to save it as hexadecimal, it's gonna be AA hexa. And remember, if I was gonna write this in hexa, and this is, I'm gonna do this AAH, meaning hexa, but I'm not gonna save the 0. I'm not gonna save the 0. The 0 comes before any hexadecimal number if it's a letter. And this is gonna be num1. I'm just think of labeling this as num1, this address num1. Now I'm gonna have num2 as word, and 255. What's 255? It's what? This is 255 decimal, and binary is gonna be 0 1 2 3 4 5 6 7 8 1 2 3 4 5 6 7 8. So now which one is the lowest significant byte? It's this. So I'm gonna copy, save it at the lowest address. This is little Indian. We're gonna always apply little Indian, guys. We're gonna always apply little Indian. If I give you indicating that we need to have it as big Indian, that's something else. Okay, and this is gonna be what? Num2. This is num2 plus 1. This is num2 plus 0. And now here I'm gonna have array byte. I'm gonna have what here? 10, and here 15. When I have byte, I don't worry about little Indian and big Indian. So let's say array A. It's not gonna fit. Array A. Oh, let's put A. I don't need you to do that. Okay. This is array A plus 0. This is array A plus 1. Now I'm gonna have array W each of. So let's label this. Think of this as the address. 1 minute. I had an addresses 1 2 3 4 and 5. I'm having a problem with the addresses. Let's try to align it at least so we don't have any problems with it. Okay, no, 18 is better. I don't know now. Started shifting. Now we might add some numbers and we'll do the same problem. But let's see. Let's change this and do 12, and line spacing we want it as didn't change it, but why was that a problem? Okay, when we copied the zeros that gave us a problem here, but no worries. So now I'm gonna have array word as this array word, meaning each element is 2 bytes. So the first element, little Indian, lowest byte at the lowest address. So here I'm gonna have 0 0 1 0, and now 0 0, second element 2 0, and this is gonna be what, plus 1 plus or plus 2 and plus 3. And remember to always start with the 0 plus 0. I like to think of it that way, makes it easier. Okay, now I'm gonna have array D and what do I have here? Array D. I'm gonna have 1 2 in decimal. This is extra. This will give me an error. It might give me an error if I compile it. So here I'll have 1. What do you think? Okay, 1 0 0 and 0. And why did I save it like this? This is 4 bytes. A D word is 4 bytes. This is the lowest bytes. So think of it as in the same. Those are 4 bytes. Thinking of it as hexadecimal, each represent, but it's decimal. So if I want to convert a decimal to, this would be the first byte, and I'm gonna have 3 bytes of zeros. 3 bytes of zeros. Think of it that way. Okay. Ooh. D word. Either think of it as decimal, hexadecimal, or binary, but you have to convert between them. I usually like to think of it as hexa. I don't know, hexa is easy, that's why they have it. It's easy to read. It's easy to read addresses. So this is gonna be plus 1. This is gonna be plus 2, plus 3, plus 4, plus 5, plus 6, and plus 7. And here what do I have? I'm moving array W plus 2. Where's array W plus 2? So I'm moving the second element, which is a byte, 2 bytes, a word, 2 bytes to AX. And this is indexing how to access. I'm saying array W plus 2. Even if I didn't put the brackets, it should work. It should work. Because array W is going to be the address, a label. It's going to do this, which means this one. So I'm doing what? 0 0 0 0 0 0 5 plus 2, go meaning to address 7, which is this, and take a word. Why I'm moving a word, that's why I took 2 and plus 3 and move it to AX. So AX is gonna have what? Hexa. Here I'm saying array W plus 4. Where's array W plus 4? This is plus 3. This is plus 4. Even though it's array D, this is label. This is a label, so don't worry that much about it. It's gonna be this address. I shifted a lot here, yeah. I should have returned it to this. I think is better. We might have a little bit. No, it's good. Okay, so it's gonna be this one. Let's make sure to Okay, yeah. This is array W plus 4. Or even if you put array D, it's the same. Just go in here, array D, which is a D word, and I'm taking what? I have to move. I can't take a D word here, but here I'm moving a word because this is the size of this. I'm moving to a word, and this can't be applicable because this is a D word, and we're gonna figure out that. So this is not valid. We have to be careful. Not valid. This over here. If I had an array D, which is the same as saying this, it will work. If I had it to EAX, that will work. What will I move here? I'll move the 1, decimal 1. Decimal 1 meaning those four to EAX, 4 bytes to EAX. But this is what? Array W plus 4, and it's saying it's a word which is 2 bytes. With EAX it's a size mismatch. So this needs to be array D. But if I had array D as 2 bytes, array W plus 4 will take what? The first byte. Now I'm moving what? Num1 to AL. What's num1? Let's check. It's a byte. I'm moving to a byte. No problem. I have AAH, which is either this in binary or this. And now I'm moving what? Array D plus 4. Array D plus 4, this one. I'm moving this to EAX, so I'm gonna have here, think of it as this way, and I'm putting it in hex so you can. No, is it this in hex? This is the first byte, this is the second byte. It's gonna be this in hex, and it's gonna be. And now I'm moving num2 plus 1 to AL. Num2, where's num2? This one. Plus, what was it? Plus 1. This. And I'm moving a word. I can't do this because this is from another element. So we'll see a way to do it. We'll see a way that we can do this. So this is not valid. By using pointers on type and move array A minus 2. So is this valid? Of course. What? Of course not. No, it is valid. I'm saying array A minus 2, go 2 addresses below this address. This is array A. 0, 3. Go 2 addresses minus 2. Here's 1, here's 2. And it's gonna take a word num2, which is 255, and save it where in AX. So I'm gonna have an AX. 0, 0, that's 1 byte in hexa. 0, 0, that's the second byte, and I'm gonna have what? FF, FF, representing what? Those. This is an F, whereas those 4 is my first F. Those 4 are my second F. That's the 0, and all that in hexa. Okay, 1 minute. if 1 byte, 2 bytes, it's 2 bytes. Sorry, I don't know why I thought it's 4 bytes. It's 2 bytes. Now move num1 plus 3. Num1 plus 3 plus 0 plus 1 plus 2 plus 3 is array a byte, so yeah, it's gonna move to AL 10. Think of it as 0 3. Think of it as array A. Think of it as num1 plus 3. Think of it as num2. So here, let's make it okay, but num2 is a word that would cause a problem. No, it can be if it was a byte. Okay. See, this is another good example. This is a really important example, guys. Please check it. Now let's see this. Write a program that rearranges the values of the 3 double words values in the following array. So if I said this array, I have the word, so I'm gonna have, you want it in hexa, or what should we put it? Let's put it in hexa. 0 1 0 0 0 0 and 0 0. That's what? That's the one in hexa. That's the one in hexa. First element, let's say, and let's try to give them different colors. Let's make it yellow. And the second one is gonna be 2 0 2. What is the lowest significant byte? Little Indian. Keep thinking of Little Indian, guys. Don't forget that. Don't save it as what? Other way around. Lowest significant byte at the lowest address. And this is in decimal. I converted it here to hexa, and it should be in binary. But I don't want to write 4 zeros, 4 zeros, 4 zeros, 3 zeros. You do that. I'm not gonna do it. And here, what do I have? 3 0 3 0 0 0 0 and 0 0. And this is my, let's say, element 1, element 2, element 3. This is gonna be array D plus 0 plus 1 plus 2 plus 3. This is array 0, array D plus 4. So this, let's put it here. Plus 4 representing this equals this 0 2. And this is array D plus 5. I should have put it here. Plus 6 plus 7. And this is array D plus 8 equals this, or this address. You can think of them as addresses. So here, what am I doing? I'm saying rearranging them. So I want to rearrange it in this way. So I need to move the 3 to the 1, the 2 to the 3, and so okay. I need to move this here, and this here. Okay. Here's the code. I'm moving array D, which is the first element, to EAX. So now EAX has what? 1 in it. And here I'm exchanging what? Array D plus 4. This one. Element 2. Element 2 with the accumulator. So here accumulator will be equal to 2, and array D I'm exchanging. And have array D plus 4 equals 1. Equals 1. So now actually we changed this. We changed it to what? to 1. Meaning if I had here, if I had it as 1 2 3, it's gonna stay 1 2 3. I didn't do any changes to it. And let's put this as a comment, guys, meaning what? A comment is a semicolon in assembly. Those are in memory, and this is the register, so don't worry about the register that much. So here what I'm gonna have is 1 1 3 as my array. 1 1 3 as my array, resulting I had it here as this, and let's mark it, highlight it so we can know. And here is gonna equal this. This is what happened here when I exchanged. I exchanged 2 with 1. I exchanged this and this. But why did I put it in a register? Because the exchange command can't deal with 2 memory location. At least one has to be a register. Go back to the exchange command. It's really important. Now we'll exchange whatever is in EAX with array D plus 8, which is this is array D plus 8. It's the 3. I'm exchanging the 3 with the what's in the accumulator is 2. So now I'll have what my accumulator as EAX equals 3 and array D plus 8. D, I'm gonna put it plus 8, so save space, equals 2. Here I exchanged whatever is it in EAX and D4. Okay, yeah, I'm exchanging 2 and 3, so we're gonna have what? 1 and 2. This is at this step. This is how my array looks like. And now here, what do? I say move EAX. What does EAX have? 3. I move it to array D, which is the first element instead of the 1. So now what will I have? I'll have my array as 3 1 2. I got whatever is in the combinator, which is 3, and saved it here. Guys, this is really important to understand. It's easy and it's nice. Go step by step and check what happened to the array. Now here we want to write a program that adds the following 3 bytes. I have those 3 bytes. This is 1 byte, this is plus 1. So what will I have? I can say move to EAX. What am I gonna move? My bytes, or you can say my bytes plus 0, whatever you want. It's plus 0, so it's gonna take the first element. So now I have in EAX, what? Not EAX, AL, 1 byte. I'll have AL equals 80 hexadecimal. And here, be careful, I can't use EAX. I can use AL, BL, AH, BH. I need a 1 byte operand. Now I move this to, and this is a comment. Remember, I'm just showing you what's in EL on each step. And now what am I gonna do? I'm gonna say add to AL. I'm gonna add the second element, which is gonna be my bytes plus 1. My bytes plus 1, which is 66 hexa. My bytes plus 1 is 66 hexa. So I'm adding 80 and 66 hexa. I'm just gonna use this memory location to add it up, so don't think this is memory. And we can save those here, the values. This is gonna just take 3 bytes. 80, 66, and remember, don't add the 0 if there's a letter. So only 1 byte. If you add the 0, that's what, a byte and a half. How are you gonna save it? 0 and 6 is 6. We add those. 14 is what? E. So now I'll have in AL what? E 6. And now what do? I add AL to my bytes plus 2, meaning this one. I'll add it to whatever is it, AL. Now here I'll have A and 5. See what I told you at the beginning? Everything is important, so now I'm doing this. I'm adding those two. I'm gonna have 11. 6 plus 5 is 11, which is B. And E plus A is what? E is 14 plus A is 10. 24 minus 16 is gonna be 8. And now look what's gonna happen. I'm gonna E. And now what do you think is gonna happen? And I have 1. How many is this? This is a byte and a half. So AL will be what? 8B. What do you think happened to the 1? What do you think happened to the 1? Think of it. Flag register. Why do I have a flag register? That one will go there. I can't. I have to have an AL, just 1 byte. Now let's evaluate this real quick, guys. I have those, same thing, and here what am I doing? I'm moving 1 byte to 2 bytes. This is not allowable. Size mismatch. Oh, this is gonna give us a size mismatch. Either I change this to a word, change my numbers, or change this to AL. Now how about the following code? Is anything missing? Let's see. I have this byte, and I'm saying move 0 extended to AX. 1 byte. So I'm moving 1 byte to AX. So AX is gonna have 0 extended. So I'm gonna have 1 byte of zeros, and the other byte as 80. Now here I'm saying move 1 byte to BL, and then I'm adding, but here what's gonna happen? That might be right. This is no problem with this. I'm moving what? 66 to BL. That's right. 66 hexa to BL. But here I'm adding BX and AX. Is there a problem with this? No. This is what? 2 bytes. This is 2 bytes. But the problem what is in BH, the upper half of this. So here we need to do what? Move 0 extended. This will work to BX. This is one way. This is one way to do it. Or I'll put what? Move above this, or I can put here. And 1 minute, let's comment those. This is commented, remember. Or we can keep it as is, keep it as BL without the, and I can say what here, I need an extra line, and I can say move BX 0, and then I'll move the 66, then I'll take the whole BX and add it here, or I'll do the move 0 extended to BX. Either one will work. Now here I'll have move what? This element AF to BL. Same thing, so I prefer using making it easier. So here I'm gonna change it depending on what. Either way you wanna do, either to go this way, move 0 extended to BX, or do it this or do it this way, or do it this way. Either way will work, either this or that. So let's highlight those. Oh, this is one way, and this is another way. Okay. So here we finished. This is a long video, guys. It's really important. Check it, review it before. It's really important in the final. That's the only thing I can tell you. And let's pause recording.